Oh, you shared the window anyway. Ah, that's why we know it's old. If you click on. Are we muted? How do I know if there are questions online? Can somebody tell me later? Will they pop up? We don't know. No. I want to be at the end. I'm going to do it at the end. Okay, great. Yeah. Should I begin? Oh, okay, cool. Thanks, everybody. Thanks for organizing the conference, and it's all been great so far. I'm going to talk about approximate inference. Oh, it's recording, yeah. I think it's recording, yeah. Approximate inference via fibrations of statistical games. Oh no. Okay, that's fine. So if you've heard me talk before, you know that I'm interested in like natural adaptive systems, by which I mean organisms that perceive and act. And when I say perceive, I mean something like you can think of it formally as a process of Bayesian inference. So that means if you're an organism, you've got sensors like your eyes, they detect some kind of data, like you could call that data in Y, and you maintain a belief about kind of the world, not just the data, but the world as it is. And that's this thing I've called beta here, and how that world causes the sense data. So you think, okay, well, I'm standing here and you guys are all over there, and like your movements cause my perceptions, and I get this data, and I can use that to update my beliefs about the world, like what you're all doing, say if you raise a hand or something. And so you have these two things. This is like a forwards thing called a channel, which is doing prediction, and a sort of backwards thing, which depends in some way about the beliefs you started with, that say, okay, given my sense data that I receive, I get new beliefs about like what's going on out there. And if you've heard me talk before, you probably know that this pair of things, this forwards kind of predictive channel, and this kind of thing that I call a state-dependent backwards channel that does updating, is a Bayesian lens. It's a kind of bidirectional process, much like the kind of bidirectional processes we've seen, in this context of game theory. And just so for some notation, I've got this category C. It's like an ambient category of channels. It's usually concrete, so it's over set. It's something like the Kleisli category of distributions. You can think of it like that. And I write those things with a dot on them. And if I have this regular arrow, you can often think of that as a function. So it's a deterministic channel. And then there's this lens composition rule, which if you've heard about game theory or you've heard me talk about Bayesian lenses and things before, you know what this means. You sort of compose the forwards channels in the simple way as they are morphisms, and the backwards things you sort of do in the opposite direction, but because you have this state dependence, you need to sort of, the kind of more internal thing is updated with respect to the prediction of, the sort of more, the more external thing is updated with respect to the prediction you got from your more internal thing. And so you get this composition rule. And it just comes from the kind of Griffin deconstruction, effectively. So these things are called Bayesian lenses because they come from Bayes' rule. And so what I mean by that is like this. So you can attach to each of these channels C a kind of backwards thing that does an inversion. But that's just some backwards channel. Bayes' rule gives you a recipe for choosing that channel, which is particularly nice. It satisfies this law that you could phrase as Bayesian updating composes optically. That means it just composes, if you have the Bayes update of two channels, you get the Bayes update of their composite by composing the inversions of the two channels. And that's this Griffin deconstruction thing. But you might wonder, like, what are all of these other channels? We can think of those as approximate inversions. They don't necessarily have to satisfy Bayes' law. And that's useful because doing inference is computationally difficult. There's often like a large integral you need to do, and that's computationally hard. So like natural organisms don't seem to do exact inference, they do approximate inference. And what that means is if you're now doing something approximate, you probably want to measure how well you're doing at it. You need to measure your performance, say, at playing this game of doing inference. So you need some more stuff going on. And that's why I have this structure called statistical games. It's going to attach more stuff to these lenses. Okay, so that's kind of a bit of background. I'm going to tell you about where statistical games come from in a bit more detail. I'm going to exemplify them with the quantity, particularly the relative entropy. I'm going to exhibit a problem that comes from the composition of the relative entropy and the way to resolve that problem, which is by copying some stuff. And that's this thing I call copy composition. And then I'm going to show that the relative entropy and a bunch of other things they constitute what I call loss models, sections of these fibrations of statistical games. And there are various monoidal structures, but I'm not going to talk a lot about those. Okay. So another thing that if you're a kind of, an organism that has to eat, you might care about is not using too much energy. And that means, doing stuff in a way that's metabolically efficient. And those, you're made up of cells. All those cells need to use energy, but they don't want to use too much. And one problem with doing, computation is that it involves moving information around. This is why, backpropagation or machine learning on GPUs uses a lot of energy, because you have data in memory, you need to bring it into your processor, and you need to do some computation on it. But the biological systems made of cells, they don't have the ability to go and get information from cells far away very easily. It's better if the computations are done locally to each cell or in the sort of region of a cell. And that means that not only do we want to do inference compositionally for abstract reasons, but it makes sense kind of operationally too, that if we can decompose the optimization problem into into components that are kind of local and optimize those independently and sort of patch together those optimizations to produce this big optimization, then it's kind of better for biology. And so what I'm going to do to construct statistical games is attach to each Bayesian lens a loss function. And I'll tell you what that means now. So I use this letter X to denote the internal space of a model and Y to denote the sensory data, but it doesn't really matter. It's a morphism in some category. And as I say, a statistical game is a triple. It's a forwards channel, it's an inversion channel that's giving you a Bayesian lens and some loss function, which I write like L super C. And as I've mentioned, there's a structural similarity in all of this to compositional game theory, and in particular, kind of compositional game theory, which is set in the framework of systems theory or categorical cybernetics, where you have fibrations of these things. And so just as creating Bayesian lenses, in particular biographic deconstruction, gives you a fibration because you have this data and you can sort of project out the channel and forget about the extra data, the inversion. Attaching these loss functions to lenses also gives you a fibration in the same kind of way. And then once you've got a fibration, you might ask, okay, what are the sections of this thing? Are there nice compositional ways of attaching loss functions to all of the Bayesian lenses? And the answer is yes. Sections of this fibration of statistical games, or a modification of it, which I'll tell you about in a moment, correspond to important quantities in statistics. So one of those is, as I mentioned, the relative entropy. That gives you a strict section of fibration. It composes strictly. There are other sections which don't compose strictly, so they give you lax sections, but they're sections nonetheless. And those are things like the likelihood or the log likelihood or the quantity known as free energy or evidence lower bound. These quantities, they're all kind of, in some sense, sums of log or integrals of log probabilities. And I would like examples that are of different forms. Actually, I don't have many examples that are different from these. These, as I say, important in statistics, but I want kind of more sections, more ways of attaching losses to lenses that don't just come from this one kind of recipe. But so if anybody knows more, please let me know. But meanwhile, I'll tell you about the relative entropy. I don't need to tell you about the formula precisely, but I want to give you the intuition that it's like a way of measuring divergence between distributions or measures on space. that means it's kind of like a distance, but it doesn't really satisfy the axioms of like a metric. So we say divergence. It has this nice property that if two distributions are the same, their divergence or relative entropy is 0. And so it gives you a function normally from spaces of distributions. So these are like states in your monoidal category into the positive reals. But actually what we can do is index it by channels rather than states, and say, given like a point in like my sort of prior space, my internal space, I can use the channels to predict the sense data, and then compute the relative entropy of the distributions that obtain in that sort of push forward space. And so this gives you a function now just from points in the kind of domain space into the reals given to channels. And there's a thing called the chain rule of the relative entropy, and that says, okay, it sounds like a sort of compositionality law. Lots of chain rules turn out to be compositionality laws, and in fact, this one will too. And if we can almost write it something like this, it comes from the kind of, it's a bit like the kind of lens composition law. It says, okay, well, if I've got a composite channel and I've got relative entropies of their, the components, I kind of want to sum up the relative entropy of those components. And I ask, okay, is that sum the same as the relative entropy of the composites? Okay, so I have these distributions, so I need to take the expectation of the second channel, of the relative entropy of the second channels with respect to the push forwards here. That's all that's going on. And this is effectively pretty much the formula for the relative entropy, but it doesn't actually, if you actually compute this divergence on the composite channels in C, it doesn't work. And so it's not quite like this. You need to do something else. And the reason it doesn't work is that the relative entropy is like an expected difference in log probabilities. You could think of this as like a sum of log probabilities. But this composite channel in C is an expectation of the product of two conditional probabilities. And this log here, if I substitute D after C and say for alpha, you see that you've got an expectation like before the log, and you can't pull it through. What we want is to say, okay, well, this log goes here inside this bracket, so that I can get a kind of log PD plus log PC thing just by decomposing the logarithm. But that doesn't work. You can't do that. And so if we just follow the composition law in C, it's not going to work. However, if we had a different composition law which kept around the intermediate variable, the sort of operational result of that is that you don't do this expectation. You just have the joint probability over here. And so in that case, if you had some composition law which does this copying, this equation which I wrote on the previous slide, it does hold, but you have to modify this composition law. This composition law, as I say, it does this copying thing. This is why I sort of write it in this kind of ugly way with this 2 subscript, because you're duplicating data. And so you could write this equation, and yeah, this is satisfied. It's nice. But this isn't now the composition in C. It's something else. What we want to do is adjust C so that composition is copy composition. If effectively the composite channels need to somehow carry their intermediate data. This operation, unfortunately, if you notice, if you sort of post-compose with an identity, you're going to have 2 copies of your output now. And so that's not the same as just the first channel you started with. So it's not strictly unital, and that's annoying. It doesn't give you a category. But if you look here, you can say, okay, well, I've got this output. It's kind of like if you know about, say, categorical cybernetics or actories or things like that, you notice that this is like a sort of coparameterized morphism from X to Z, where the coparameter is Y. And there is a construction called the Copara construction, where morphisms are allowed to have this extra data, and they carry that around. But in this Copara construction, again, you have normal composition in C. It's not copy composition. But nonetheless, Copara is a bicategory because you have this kind of extra data in a second dimension. And so we can adjust this bicategorical structure to account for this copying. And because it's a bicategory, you're allowed to have kind of weaker composition. And that means that you can have this weak unitality. And so the horizontal composition here in this bicategory that I call Copara 2 is copy composition. The two cells are something you could call changes of coparameter. One thing you can do with those two cells is like discard the coparameter, do that marginalization, and then you recover C again. You've got structure morphism, as I say, they sort of do the bookkeeping. The trouble with the construction that I've got here that I'm talking about and the one that's in the paper is that it's kind of quite ad hoc. I just took this copara thing and I adjusted it to make it work, and I proved that it satisfies all the axioms of a bicategory. It's not very elegant. It's good enough to do this thing with the fibrations of statistical games, but it's kind of not somehow universal. And I have since discovered better ways of talking about coparameterization, or this copy composition thing, which is more sort of suited to what's actually going on somehow under the hood. But because I know that this thing gives me the fibrations that I want to tell you about, I'm still going to tell you about it. It does the job for the story today. I've got a slide at the end where I tell you a slightly different version, which may be a bit better. Okay, so now I started off by telling you that, okay, we've got Bayesian lenses and they were living over C, and that these things form fibration because I can project out the morphism, the sort of predictive morphism that I'm starting with, to which I'm attaching my inversions. And now I've got a second fibration, which is the fibration of statistical games, and it lives over Bayesian lenses, again, by attaching loss functions. I'll tell you the type of the loss function soon. But now these are really fibrations of bicategories, or two fibrations, something like that. And so that we've got this tower of fibrations like this. This discarding map, the one that's denoted by ground, to adopt a symbol from, say, categorical quantum mechanics, is the one that I mentioned, which throws away the intermediate variables by marginalizing over them. And that's the thing that recovers C. And there's a sort of lax inclusion of C into this bicategory, which just takes each channel to itself. And it's lax because the composition is going to give you the copying, blah, blah, blah. And this thing is a section. It's nice. So if you include it into C and you throw away the copies, by marginalizing, you get back C again. And Bayesian inversion, exact Bayesian inversion, gives you a section of the fibration of lenses. I call these inference systems. So you might have another way of doing inversion or assigning inverse channels to your predictive channels. And those could be sections as well. Those are things I call, as I say, inference systems. And then we could ask about the sections of the second vibration. And those are the things that I call loss models, and the relative entropy sort of classifies one of those. The results about Bayesian inference that I've talked about before, that Bayes' rule satisfies this kind of lens-like compositionality property, still hold here. There's a kind of sort of co-parameterized version of Bayes' rule, and it still satisfies this nice property. But the main thrust of the talk today is about these loss models and these loss functions. So what are they? How does the relative entropy fit in? And so I can tell you about that now. A loss function is going to be a way of saying how good my inference system is at doing inference. It's a thing that takes in the sort of prior belief, the thing that I have in my head about the world, and the data that I get from the world, and it says how good is this lens at actually inferring stuff about from that data. This sort of the domain of this loss function is a bit like what's known as the context in open games, if you know about that. But it's not quite the same. It's the data you need to plug into your lens, and it gives you a real number. So the relative entropy that I started with gives you one of these. We'll see in a minute. The way I do it with the relative entropy is to consider the relative entropy of the inversion with respect, the approximate inversion with respect to the exact inversion. But I want to tell you a bit more about the sort of abstract structure of these before I give you those examples. And so what we want to do to make this fibration is to plug these into, to consider these internally to C. And just as the inverse channel of a Bayesian lens is a state-dependent channel, a loss function in a category where you've got sort of non-trivial effects or co-states, you can consider that as a map. A co-state in a copy discard category is often like actually witnessed by a map into the sort of underlying field of scalars, the sort of positive reals in the case of classical probability. And so if you have a category with these like non-trivial effects, they correspond to maps into R+. We need like a state-dependent effect because again, it depends on this prior belief. And so we can internalize this to a map like this, and this is a function that says, okay, I get a state and I give you back a map into the sort of reals that depends on Y. There are some other conditions which I call having bilinear effects, which effectively means that the effects are like a commutative monoid with respect to this copy composition thing. And so there are some example categories where this works. So this works in the Kleisli category of a free module monad. It doesn't work in the Kleisli category of distributions or subdistributions. In distributions, it doesn't work because you don't have any non-trivial effects. In subdistributions, it doesn't work because you don't have stuff that satisfies the axioms, but it doesn't matter. It's easier to work in sort of this kind of unnormalized case. And similarly, in sort of measure theoretic probability, you can work with S-finite kernels. Each of these spaces of effects is then a monoidal category. It's got morphisms between effects given by their differences. You can sum up these loss functions, these effects, and this gives it sort of this monoidal plus structure. And we can extend this to the loss functions, the state, you get state-dependent differences and state-dependent effects, and it's all nice. So we can express the examples I mentioned earlier as loss functions. As I said, for the relative entropy, you take your forwards predictive channel and the exact inversion and you compare them. The log likelihood, you just take the log likelihoods of the distributions of the forwards channels. And the free energy is given by just the sum of these two. And so those are nice ways of like writing down these quantities which come up in statistics in this kind of lensy language, and it sort of, in principle looks nicely compositional, but I haven't actually told you how they compose and like how the chain rule arises. The thing is, it composed like this category of statistical games is obtained by Grothendieck construction, and so the composition law of these loss functions is just the composition law that you get from that Grothendieck construction. And so really it's just like the way you would compose the inversions themselves. You do this thing I've mentioned before where you take the loss of the first channel and you add the loss of the second channel, like expected under the prediction made by the first channel. There are these complicated formulae, but it's not very complicated if you just sort of draw some pictures and sort of follow the information through. But it's that story that I told you. You're just really adding up the losses on those two channels. And that's, this formula here, it's this expectation and this other thing here. So the loss models assign nicely compositionally these loss functions to lenses in a way that is compatible with this composition law. That's what it means to be a section of the fibration. And so effectively that means that they satisfy this chain rule. And so in this case of the relative entropy or Kullback-Leibler divergence, you just have the decomposition like this. And it is just the chain rule. It's a slightly different chain rule because I'm considering these systems where you have a sort of predefined inversion map that you want to compare, but it's exactly the same really. And we can talk about how it works later. As I mentioned, these loss models, they're not all strict sections. The relative entropy does give you a strict section, but because we've got morphisms between loss functions, their differences, we're allowed to consider like differences between like the composite of two loss functions and the loss function assigned to a composite, and that's how we get lax loss models. And so, the maximum likelihood or the log likelihood loss model that I mentioned is an example of a lax section, a lax loss model, because there's some data you're not sort of taking into account, and you can still take that into account in a nice compositional way using the sort of structure of this fibration. This gives you morphisms of loss models. They are things called icons in two-category theory. You don't need to know what that means, but they are effectively capturing these differences. In the paper, I spell out obviously precisely what that means. But that's not the only kind of laxness. Obviously, as I mentioned, we have these monoidal structures, and these are similarly often going to be lax. The category of channels that we started with, of course, we're doing copying, so you have two things side by side, so that has to be monoidal. As a result, this bicategory of copy composites or coparameterized morphisms is also monoidal. As a result, similarly, Bayesian lenses are monoidal. I'm almost done. And so statistical games is monoidal, and they're also monoidal in a way from inheriting structure from C, and that's very standard. The loss functions have a monoidal structure, as I've mentioned, they sum, and that gives you the monoidal structure on loss models, the category of loss models, that's this loss of C. And that's how I can define the free energy loss model as the sum of the relative entropy loss model and the maximum likelihood loss model. And so that's nice as well. And again, that summing, of course, satisfies this nice compositionality property. It's all nicely compatible. But there are also monoidal structures on the loss models themselves. If I have two channels, like two predictive channels, say I've got a left eye and a right eye, I can make predictions about what each one is perceiving in parallel. And I can measure the performance of those predictive processes. And that makes the assignment of losses on those channels compatible in some sense with that monoidal structure. And that means that those sections are themselves lax monoidal lax sections in general of this fibration of statistical games. And so we have this category of monoidal loss models, which is also a monoidal category. Anyway, so there's a lot of these structures and they're all lax. The reason they're all lax is that if I have two eyes, but I might have a sort of belief about what's happening on the left and what's happening on the right that's correlated between them. But if I just invert the two parts independently and I ignore those correlations, then I've missed out some data. But if I invert them together, then I'm able to sort of incorporate that correlational data. And so just considering them in parallel isn't somehow enough, and that's why they're all lax. So earlier when I introduced the relative entropy, I said, okay, you can just do it on parallel channels. Here I was saying you have the relative entropy between your inversion and the exact inversion, and that's how it works with lenses. It is strict monoidal on just parallel channels. And if you look at this remark in my thesis, it explains how that works. So we talked about statistical games. They formalize local approximate inference. It gives you a fibration of over Bayesian lenses. I introduced this notion of copy composition to get a way to incorporate this chain rule of the relative entropy in a way that actually works. And I told you about some other statistical quantities and how they give you lax sections and monoidal structures. There is this extra slide, which I can tell you about if you're interested, about how to do copy composition more nicely. But it's something that I'll tell you about if you're interested. And thank you.
I'll make sure we have time for one quick question. Just shout it out. Oh, yeah, go ahead.
Just thank you. And a point of, I want to make sure I don't remember what you said. F divergences are a whole class of divergence functions. Which, yeah, I'm not sure if you were interested in those, the generalize the Kale divergence.
Yes, I am. Other F divergence-like structures often have some non-trivial exponents in them, and it's hard to, again, pull the log probabilities through those exponents. So I don't yet know how to incorporate them very precisely into this structure, although I imagine there is probably a way to do it. I'm not totally sure of it, though. But it still is an example of a kind of log probability-esque section, if it is a section. It's not I would kind of like Wasserstein distances to work too, but I don't know how to do that.
Well, I'm looking forward to your talk, the next talk you give on factor graphs.
Yes.
That is